Thank you so much. Thank you so much, Beverly. So I just showing some video of our spacecraft lab where these both spacecraft, fully autonomous, finding the right path, avoiding collision, and then eventually they are doing docking. So the main topic of today's talk is trying to kind of figure out what's the role of aerospace department in this era of AI and machine learning. And so I'm going to mention some of the strategic paths that I have taken along with our colleagues at CAST and GALCIT. And then basically it's going to be a high-level overview, but obviously it's a crime not to show any math equations in a GALCIT colloquium. So yes, I do have some equation, but I try to make this presentation at a very high level. So always I run out of time to acknowledge my co-authors and so on. So special thanks to my CAST colleagues. I do have a lot of machine learning and control theory combination of those intersection with Yi-Sung Yu and Anima and also Joel. And I have a strong collaboration with JPR Chief Technologist Fred Hadaye, and Maury, Sergio, and all the CDS and GALCIT faculty. Thank you so much. And then this is the Zoom screenshot from my group actually celebrating Serena's birthday yesterday. So CAST has a couple of 5 moonshots, and I'm kind of focusing on 2 moonshots. And first one is actually multi-agent robots, or comprised of maybe multiple swarms of spacecraft and drones. So recently, I actually was a guest editor for the top robotics journal called the Transactions on Robotics, and I kind of illustrate all the research directions and prior work in the area of motion planning, which is oftentimes called the guidance in the aerospace community, and feedback control and perception, navigation. So you might want to check that out. Before I talk about main topics, I'm going to briefly talk about my spacecraft swarm. I've been working on this spacecraft swarm starting from my PhD work, formation flying. So swarm here means that maybe potentially more than 5 or 10. So the number could be large, or your methodologies or technologies of guidance or algorithms or autonomy or technologies should be scalable to more than 5 or 10, up to very large number, like tens or thousands of spacecraft. So I'm very happy to let you know that we have a potentially breakthrough flight demonstration. It's surprising that we have yet to see any formation flying demonstration that involve more than 2 or 3 spacecraft that do full advanced autonomy and so on control. So we are working actively with the JPL and also corporate partner to launch 3 CubeSats using this big spacecraft. It's called the Cygnus by Orbital Science, now Northrop Grumman Innovation Systems. That is the main International Space Station supply vehicle. So after the end of the ISS mission, it's going to launch our 3 CubeSat. And along with this Cygnus, the 3 CubeSat will do kind of a autonomous reconfiguration and so on, using very advanced computer. And because we are not going to put the radiation hardened computer, which is typically very expensive. But this computer is called NVIDIA, where I shouldn't maybe mention a company name, but this is a very powerful computer with a 256 GPU cores and 2 gigahertz ARM-based processor. So it's going to blow anything out of the water in terms of computational power, whatever computer you see in space now. So it's going to be like a really breakthrough technology demonstration. We are very excited about this. And then we are going to talk, I'm going to talk about a little bit about some of the guidance and control technologies we can pursue to demonstrate that. And I have to mention that we have a lot of excellent research going on in the perception area, computer vision and estimation, especially for swarm. But I'm going to mainly focus on control and navigation, guidance problem in this talk. And so this project name is called the Castor. And we'll have a presentation coming up, by the way, June 4th. And our AE105 students are working on this project. Yeah, so I said I'm not going to talk too much about the navigation, but one of the important aspects of this swarm is obviously led by Kai and Serena, how you figure out the location of the spacecraft, and even how you actually create the model, 3D model of your neighboring spacecraft or target spacecraft, like a Cygnus. So we have a fully consensus, like a distributed control, estimation algorithm that can actually figure out the location of your neighboring spacecraft without using GPS. But we have an algorithm that can actually use both GPS and computer vision-based math. And this is from our new spacecraft lab, obviously. So another important aspect of this method or a project is to figure out the safe and right path and trajectory for individual satellites. And there is no central agent. So you can see that we are running our real-time optimal control algorithm. Optimal control here means that essentially you have a certain time cost function, integral of a certain cost function like a fuel expenditure over time, while you avoid the collision and various state and input constraints, and eventually they have to achieve the objectives. So I kind of, my research group's work is kind of the first work step using this sequential convex programming to solve the very complex real-time optimal control problems involving multiple spacecraft. We have a number of papers, and recently we extended that to more rigorously include linear dynamics, and we started also working on the stochastic dynamics with the chance constraints I'm going to talk about soon. So this is kind of my main message, and it's a kind of busy slide, but I'm going to show this slide oftentimes today. So the big box right here is the real-time planning, motion planning. Typically it's called the guidance. So this is the method of finding the optimal path connecting your initial point A to final desired point B. But if you have a multiple of those, like swarms, then you have to figure out also kind of cooperation and collision avoidance and so on. And then we have a conventional controller, like a feedback controller, but I'm going to show you how you actually use the some rigorous stability proof and optimal convex optimization to find some stabilizing optimal controller or using some convex optimization. And then more recently, typically this learning and planning and control and estimation were kind of disconnected, but eventually once you have to figure out the missing part, which is highlighted here is G, that can be viewed as an external disturbance and modeling errors and whatever kind of external terms that have to change on the fly. How can you actually estimate those? How can you learn those offline if you have a lot of data? And then more importantly, how can you actually accommodate the real-time changes on the fly? So that's going to be real-time learning. And how you integrate all these in a very mathematically rigorous stability theory and safety analysis for both deterministic nonlinear dynamics and also recently stochastic nonlinear dynamics. Eventually, after all the dynamics are nonlinear and stochastic, right? So we are going to go into each block and how we integrate those as a kind of a path forward to the learning and more autonomous guidance and control and navigation algorithms. So this is the slide from my 2009 presentation. And here the main message was as follows. Yes, if you look at the brain, we have a cerebral cortex that does the unsupervised learning, and this is actually conventional method, right? You have a combination of unsupervised learning and supervised learning from cerebellum and the basal ganglia, which is responsible for reinforcement learning, right? And all these blocks together, you can generate very kind of potentially fully autonomous, very capable decision-making and even just control. And at that time, I was actually emphasizing two things. When you want to reverse engineer central nervous system like humans and animals, because they can do a lot of complicated motions and movements, even compared to some of the best robots we have out there. But where is actually a discussion of a sensory motor system or spinal cord? But the central nervous system doesn't really mean just a brain, but also includes the spinal cord that can actually do a local loops to control your limbs and joints and so on, right? So that was the main motivation, right? Yes, each neuron has like a millisecond delay. And if you know the control theory, even just millisecond time delay can really screw up your stability and performance of your high performance control system. And then we have a millisecond delay in each neuron, and we have a human adult has roughly 100 billion neurons. And collectively, we have roughly then 2 or 3 seconds of delay in this kind of response. And you have a sensing system, then you have to react to that. So it's a very clumsy and non-high performing system, but we can actually do a very complicated task. So my point here at that point was that, yes, we should not just look at the learning and very complicated learning and brain system, but we have to also focus on how you actually combine this kind of learning and control system with a low level, like a spinal cord, where you can actually do a very fast decision making for actual hardwares like sensors and actuators. So that was actually my point here, and that key idea is a hierarchical combination that can be used to really help this time delay we have. So that's the second point here. So that led to some of my flapping fly, because the idea of this flapping fly was that at that time, in the robotics community or even aerospace community, everyone was looking at the very simple like a flapping flight model in terms of not aerodynamics, but in terms of mechanical and robot dynamics, where you have only flapping and pitch. It's basically insect scale model. So what about bats and birds, where they have like more than 30 joints on their wings? So it's very complicated mechanical robots. So how are you going to control those like mechanical joints, complicated joints? So the idea was that, yeah, let's actually try to think about the reverse engineering central pattern generator on a spinal cord. So that actually led to my Air Force Young Investigator Award and some of the best paper award. So we kind of developed a mathematical model. It's actually composed of coupled limit cycles, then using some stability theory to prove that, to control these phase differences between these multiple oscillators. And so this is actually still kind of actually this is the first paper that uses a central pattern generator based controller for flapping flight. When you have a multiple joints, not just flapping up and down, but you have like lead lag and independent left wing and right wing. So this is still kind of a focus on this philosophy of how you actually reverse engineer the sensory motor control or spinal cord part of the central nervous system, not just brain. And I don't know if you know this work. So also we applied that to underwater robot. It's actually turtle robot, and it has 4 limbs, and each limb has a flapping and pitch. So it has 8 in total degrees of freedom, and we can control the phase difference between these limit cycle oscillators to control the attitude. So you can view this as almost like a gait of your walking or running quadruped or a biped. You can control these phase differences between multiple oscillators to control the attitude and position of this underwater robot. Oh, so I'm skipping. So the end result is obviously this backboard. So we wanted to apply some more sophisticated controllers. So this backboard is actually still, in my opinion, state of the art, because it only weighs 93 grams. It has a microcomputer that can do low-level control loop, and it has actually as many as like 6 fully controlled the motors with an encoder feedback for flapping and wing folding, independent left and right wing folding. And so that's kind of my culmination of investigating bio-inspired control approach. Still, we designed a very nice nonlinear controller, but it didn't really have a learning part. It didn't really have a sophisticated autonomy. And then I actually wanted to show this one. I'm sure that because we have a lot of fluid mechanics colleague, and with a Kenny Breuer, at Brown, I was invited to some Spanish program called the El Hormiguero, which means the ant, with the Hollywood actors to present our robotic bath. So this is the old approach. We have a feedback control here, and then we have a plant, whether it's linear or non-linear, and we have a separate motion planning. And the idea was that just try to design a controller, and you can check the stability, whether you can check the eigenvalues. Checking the eigenvalues is essentially finding same thing as finding the upper function for nonlinear system. And then we can actually have a input-output stability analysis, like the LP stability for linearized system. So my next step is that how can you integrate all these different pieces? And what about learning? And this is more of a robust control. I mean, you can add adaptive control, but what if you have a certain block here where you highlighted by G, either it's actually unknown wind-based disturbance in terms of aerodynamic force and aerodynamic torque, or it could be some like unmodeled structural vibration, and because of that you have additional like a disturbance entering your system. It could be anything. How can you add a learning so that you can actually have both feedback control and estimation, and at the same time even motion planning, which is not typically benefiting from the learning-based process? Because I'm going to talk about that, the ramification of that. So this is my proposed approach, and I shouldn't say my, because this is some of the approaches that we are pursuing along with our CAS colleagues, and a lot of students are working in some of the intersections. So there is like a learning, offline and online learning block that can kind of help the better trajectory for motion planning in terms of collision avoidance and safety and minimizing the fuel. Also, you have to have very stable and safe nonlinear feedback controller. So we are benefiting from some of the recent updates that can even analyze the nonlinear and stochastic dynamics of both nonlinear control and estimation problem. Estimation here, if you are not familiar with this kind of control theory, estimation is basically figuring out your state, x hat, for example. Then control is obviously figuring out the u, and the learning is basically whatever parameters and the disturbance and unmodeled the errors you can actually add to your system, and it's about the estimating those, either real time or offline. And you can have a combination of those. That's what I'm going to talk about too. So this is a little bit cheesy, but this is a pelican. It was actually stranded in Tanzania in Africa because of a storm. And it even kind of forgot how to fly, how to flap the wings. I mean, can you believe it? And then quickly it kind of realizes, oh yeah, you have to move the wings here like that and so on. So it starts flying beautifully. Several things that I want to mention here is that these kind of birds do not have a vertical tail. So if you know the flight dynamics and stability, typically you need a vertical tail and rudder to control the basically directional, the heading or yaw stability. So how can this kind of bird or bat fly very efficiently and control it without any vertical tail? So the idea is that basically dihedral. Dihedral means that wings are kind of upward, but you can actually move the dihedral angle and control it. It's like a flapping, but you don't flap in the oscillatory fashion. If you can control the left wing dihedral and right wing dihedral, then you can control that difference to actually generate the yaw. So this is actually the first kind of robotic experimentation and the controller demonstration of a vertical tailless aircraft and then perching, so they can automatically figure out the location and then do control and then land gracefully on a human hand. And so this actually involved a very sophisticated control design and combined the guidance and feedback control and proof stability. Actually, we used a certain technique called nonlinear direct inversion and then singular perturbation to kind of do a hierarchical decomposition. It looks beautiful, but my point is that it really lacked some more robust, like autonomy and learning-based black box, because it didn't try to really learn any uncertain aerodynamic forces and the location changes of your target location. So how can you add this kind of a learning block into this kind of a sophisticated nonlinear flight control design. That's something that we are pursuing right now. So I'm just showing you the prior work. I'm just taking this opportunity to also talk about, I talked about swarm and multi-agent system, either for spacecraft and so on. So combining this kind of flapping flight dynamics that I'm now familiar with, and how you control this drone, like it looks like a bird. And we kind of got the NSF funding to actually find a solution to herd a flock of birds that actually tend to fly around the airfield, and actually causing all this accident. As you can see that this kind of miracle of the Hudson River, they actually had a spectacular landing on Hudson River because they were lucky, and the captain knew how to do a gliding flight. So this paper, we actually presented some mathematical model of flocking dynamics of bird, and how can you reverse engineer a mathematical model of this flock of the bird's behaviors, like a cooperation and following the leaders. How can you actually add an intruder to herd the flock of birds in reality? So this is the first real demonstration of a robotic drone herding a flock of birds using our mathematical algorithm. And obviously, it wasn't, and I wasn't sure that it was legal to do that in the US. So we actually collaborate with some international institution for this. So going back to the main message, how you kind of combine these learning pieces for both guidance here, which is motion planning, and feedback control and estimation. So we are going to start with motion planning, which means that optimal control and guidance problem. I'm saying that you can use the optimal control to solve the motion planning problem. So typical way of solving this problem is that you have a cost function. Either you have minimizing certain fuel cost or energy cost. You can add additional cost function, and you have a highly nonlinear dynamics, and then you have an input constraint, and you have a various safety constraints, typically like a collision avoidance. So the collision avoidance here means that you have to have sufficiently large distance between the agents, and then this is a typical problem. You have to start from certain initial condition, but then you typically give the final terminal time set. What's unique in the swarm problem is that you might not actually give the terminal constraint. Instead, you might actually give a certain condition, like why don't you make this particular shape? Because you don't really care. If you look at this diagram here, spacecraft number 6 going to this location, it doesn't really matter as long as you can actually reshape the original formation to whatever desired formation you're looking at. The more recent work, we started to actually develop some method of using sequential convex programming, which can be run very fast in real time for many applications. And we can actually solve the variety of real-time motion planning and guidance and control problems that can be running on board. We are running them, a lot of algorithms on board on our computers, so it can be very efficient. And typically, it took a lot of time to solve this kind of problem, especially when you have more than one agent, and also highly complicated nonlinear dynamics with many states. Now we can solve this very efficiently. Here, what I'm saying is that we have a bunch of extensions and kind of stability proof and convergence. And one thing I want to mention here is that when you have multiple agents, then the terminal constraint is not given. Like here, I said the target assignment. So you can also combine that target assignment problem, which can be using some existing methods like Hungarian method or whatever, like game theory-based method. Basically, each spacecraft, each initial position, you are figuring out the best optimal terminal point to achieve your goal, and that can be viewed as another optimization problem. But you have to kind of simultaneously integrate these both methodologies of optimal control, basically finding the path. I'm going to mention this particular word, path or trajectory, multiple times in this talk. So we have to kind of combine these multiple trajectories and what's the initial condition, what are the terminal conditions. So that's for the target assignment problem. And we have now some combined methodology, we can actually do that. One thing I want to mention is that you are finding the single point And that's another decision problem. And that's actually one example of a hierarchical combination I started talking about. And I talk about the central nervous system and brain, how these complicated machines or animals do work, because you have a very complicated networks that are essentially hierarchical. They can do a fast time decisions and slow time decisions, fast time movement and slow time movements. So we have this, from the theory of stability and dynamics, we have some perspectives that we can leverage for achieving this hierarchical combination of very complicated dynamics. And I want to mention that essentially this target assignment problem is essentially learning problem or decision-making problem that can run a little bit slower, because you need to figure out only at one time step, which is terminal time, instead of many independent time steps between initial time and terminal time. So that's actually another example of how you combine learning-based decision with the optimal control, feedback control problem. So this end result is that you can generate a many complicated shape from whatever initial condition, and you can lose some of them. They can autonomously figure out where to go in a collaborative fashion. So those like dance circles actually indicate communication radius, the communication where you can actually communicate with other agents. Some other extension is that something that I didn't mention is that in order to actually make this as a convex optimization, but sequential, so that you can actually handle a little bit more non-convex constraints or dynamics, including nonlinear dynamics, we actually use the hyperplane approximation. So you start drawing hyperplanes to avoid a collision, but that may be too conservative. So what we are doing here is that you start expanding the collision avoidance like a spheres. So it's gonna look like a tubes, expanding tubes. You can actually define the collision-free, safe region. So again, this is kind of illustrative, right? You are moving around a very cluttered environment, and you want to figure out what's the best optimal collision-free path. Then you can figure out heuristic approach using the RRT or tree-based approach to find certain path, and then you can start expanding the spheres along that path, and then using the dynamics, using sequential convex programming or optimal control solver, they can actually guarantee some feasibility and dynamics constraints, satisfy the optimal solutions. So here I'm going to talk about now how we can add a learning part. So one extension is that I only talked about the deterministic nonlinear dynamics. Again, I can tell you that if you actually add a nonlinear dynamics, I'm not talking about stability problem. You have an optimal control. The typical way of doing that is that you linearize the nonlinear dynamics, but you do that sequentially. So you start improving the linearization errors, but there is no way you can actually handle nonlinear equality constraints because nonlinear equality constraint means that it's non-convex, right? So there are several extensions of doing that using the nonlinear correction paper. Second thing is that now what if you start adding the stochastic differential equation? So which means that G here is unknown because your optimal control solution is optimal with respect to your known model, known dynamics. So if your known models are not correct, then your optimal solutions are not correct. And which means that you might actually violate safety constraint like a collision with an obstacle. So here what Yashwant did was that really looking at how you actually use both stochastic nonlinear dynamics and chance constraints. Now your collision avoidance constraint is now formulated as a constraint chance with a chance, which means there is now probabilistic constraint. So what's the chance or probability of like disobeying or violating this particular collision? So you write that as a chance constraint, and then how you actually solve this kind of very complicated optimal control problem by turning this stochastic differential equation to the deterministic nonlinear equation using polynomial chaos approximation. It's almost like, since you are fluid dynamics and solid mechanics experts, it's almost like very similar to the GALCIT projection, where you kind of turn the PDE into ODE. Here we are turning the stochastic differential equation to the deterministic nonlinear differential equation, then you start applying the standard method. The challenge here is that you have to also handle the chance collision, probabilistic chance constraints that are written in the original state, but you have to convert that to the now projected this deterministic state X. And then you can see that depending on the noise, you can kind of find the path, which was kind of very aggressive here, but if you have a lot more noise, you can actually find the other path in the right-hand side, if you look at this bottom left figure. And the new extension of that is that along with the Anima, Guanya, and NG, and Yisong, we are actually learning this G in the real time so that you can improve this kind of learning. And so it's kind of an exploration and exploitation trade-off. You want to make sure that your optimal trajectory is optimal, minimizing the optimal cost. At the same time, you want to move around so that you can learn more about the dynamics. You can collect a more persistently exciting data. So that's actually an interesting paper we are coming up with, and hopefully it's going to be accepted by this. So now I'm talking about some now new application. Before I talk about some of the theory here. So this is a flying ambulance, and this is also one of the most important moonshot. When I actually luckily got involved with the cast, I kind of look at all this kind of exciting research going on in various aerospace institutions, and then I kind of try to figure out what's the next step. So we have like a drones with the wings, and we have a bunch of quad rotors, and we have helicopters. So I thought that maybe by building on the advances in electric motors and drones and multiple propellers, maybe you can kind of combine the wings and distribute the propellers so that we can actually have a more range than just quad rotors. And also it's safe, much more safer than just conventional single rotor or double rotor based helicopters, because you might record the very unfortunate and sad crash of the Kobe Bryant helicopter. Helicopters are very well known for unreliability and so on, because you have to basically essentially rely on single rotor or multiple couple of rotors for safety. Here, the objective here is that instead of having these kind of meat grinders, you have distributed propellers that can actually get you the safety. How you connect point A to point B safely, either delivering packages or even humans. Under any weather conditions, obviously we are basically benefiting from this kind of a very fancy 1,296 computer fan-based fan array, right, to generate all these different sorts of wind disturbances. So I want to reflect on why flying cars, by the way, because the fast flying ambulance is one example of flying cars. The idea here is that I wanted to actually contribute to this AI and autonomy of self-driving cars, and this is an important problem. But if you know how to find a solution to make these autonomous flying cars, I thought that that could be also applied to self-driving cars. But more importantly, I don't know when we can have a fully autonomous car networks, because eventually you cannot completely get rid of humans, the pedestrians and the cars driven by humans, and that's going to cause a lot of problem, because although you might have a very advanced intelligent cars driven by autonomy engines, you might not actually get into this conflict with the cars driven by humans. So why don't you actually try to utilize three-dimensional world? So that's the one motivation for self-driving flying cars instead of self-driving cars, where we can do a lot of autonomy-based research in the aerospace world. So our vision is that let's develop this kind of drones that potentially have multiple propellers for robustness, and we might have also multiple hybrid actuators and control surfaces from the wings. And then you have to have this kind of autonomy that can connect point A to point B that might be delivering certain packages. But here is the point is that, do you have any delivery drones that can actually survive any weather conditions? We don't, because you try to fly the drone and heavy wind, it's still very challenging. But once you start carrying a human passenger, you might want to make sure that your drones are extremely safe and robust, right? So we are going to actually show you some of our cast and machine learning and control research problems, how they are related to solving this kind of a very autonomous and safe drones that can even carry humans. So one problem is that as I said, the idea of these multiple propellers means that, yes, we know the aerodynamics, the thrust coming out of the propeller is proportional to the diameter of horsepower, whereas this is proportional to the only motor speed squared, right? So I can see that the benefit of expanding or increasing the rotor size, we might end up doing that, but we want to make sure that each rotor blade are less harmful, less intrusive. It's not going to be a meat grinder. At the same time, can you, I mean, have you known that if you actually fail one random propeller out of a hexacopter, it can just easily destabilize the system. So you need to have a certain configuration, either tilting and a certain right controller. So we are kind of demonstrating the fault tolerant controller that can restore stability in the presence of random rotor failure. That's only possible with multiple rotors. So that's one kind of condition. Here, second problem is that how can you mix the fixed wing based flying car concept with the multiple rotors, whether quad rotors or hexacopters or 10 rotors. So we have worked with the Morigari's group, and then this is actually airplane autonomy test bed for flying ambulance. It's not really flying ambulance model, but it has a 10 rotors, it has a fixed wing. So we actually successfully demonstrated the full 5 mile, 2.5 meter back-to-back fully autonomous flight from all the way from the taking off and landing. And you know that it's illegal to do that because you have to maintain line of sight. You can see this kind of mini car just in the video. We borrowed the car, open car, and the people, including Reza Nemovi there and Patrick, were following this drone, made the visual line of sight, and we fully demonstrate this transition flight going from the taking off and hover and flying like a fixed wing and coming back. So that's one of the technology, but obviously what's happening in the very benign weather conditions and no uncertainty. I mean, we had a relatively controlled environment. So how we can actually improve this kind of robustness, and what if it's carrying unknown mass, unknown heavy mass? Then you have to make sure that you can actually accommodate this kind of changes, right, in your model. So that's kind of roughly the problem. So this is kind of an evolution of our previous flying ambulance model, including some of the recent autonomy testbed. And then I have to acknowledge that some of the earlier designs were done by Ji-Chen, my PhD student. And we are currently working on AFA 4.0 that actually improving on all the lessons we learned out of this exercise. So again, some of the control problems, we have to figure out this transition flight. And if you recall this, is it Osprey, Boeing, tilt-rotor aircraft? And many of these challenges of this kind of a VTOL with a fixed wing are caused by this transition flight and instability. So we have a number of algorithms that can actually handle stability so that we can do a very smooth transition. And this is another example of flight control, but I want to mention that in this example of this VTOL fixed wing, it's actually a collaboration with AeroVironment, Phil Tokumaru, which is who is actually GALCIT PhD under Dimotakis. And we actually, students actually developed the 3-dimensional flow sensor that can actually measure the angle of attack and the flow speed and then side slip angles. And then once you measure those, that's fine. And you remember this, like a Boeing, the accident, the crash. You can measure with this like angle of attack and so on. But the thing is that how you want to measure and incorporate this measurement, not just only angle of attack, but side slip angles. And then you use that for like learning-based flight control. That's what we did here. And so trying to kind of adapt to these learning-based flow measurements that can actually lead to the real-time learning. And we are here using, instead of a full-blown learning-based method, we are only using adaptive flight control. But this is quite promising in the sense that it can kind of handle its various kind of disturbance, right? In order to actually generate this disturbance with a varying speeds, because we don't have that capability yet, actually they came up with the idea that they can actually change the tilt angle. You can see that, right? Thereby actually changing the like a flow speed around the aircraft. And we actually demonstrated the really kind of one of the first full transition flight from hover and to the fixed wing flight, because hey, any rotorcraft like this can hover like that. No, this is actually, we are flying this as a fixed wing aircraft based on the wind generated by the fan array, which means it's almost like a wind-based treadmill, right? Which is kind of awesome. It kind of shows the benefit of this kind of test bed where we can actually do a even transition flight between VTOL and fixed-wing aircraft using this test flight arena led by Mori and his students. This is also an exciting project. Okay, so you develop flying ambulance, or you modify that for maybe next generation Mars helicopter, but your Mars helicopter may land on uneven terrain or very challenging. So the key idea that we are looking at here is that how you actually combine, like I'm combining fixed wing with our multi-rotors for VTOL, we're trying to combine the propellers with our legs. And legs can be viewed as kind of locomotion actuators, or it can be viewed as an adaptive legged landing gear for flying ambulance or a Mars helicopter. So how you kind of do this flight control with the leg control. So we are actually generating some exciting results. Now it can actually work very well, but we are writing a paper. So we have a roughly maybe 10 or 15 minutes. So with all these challenges, I now want to talk about how you combine the machine learning with a flight control. And people have used this method, but typically machine learning or AI are typically synonymous, unfortunately these days, with a big complex neural network, either deep neural network or for vision problem, you have a convolutional neural network. What he did here is that this particular technique called the spectral normalization existed in the machine learning community to kind of bound your black box. But then working with the Anima's group and Yisung's group, our PhD student from GALCIT and CDS, Wanya, Ji-Chen, and Michael O'Connell, actually developed a very stable flight controller that can actually use machine learning to learn the unknown dynamics. And then using spectral normalization, because once you know how to bound your black box, AI or deep neural network, you can use that norm bound to design the stability proof for nonlinear system. So that's why exactly what I did. And the problem here is actually very interesting because it's kind of a aerodynamics problem. Once you land your aircraft, whether it's a fixed wing aircraft or a drone, you actually have a ground interaction, which is called the ground effect. Or the kind of a simplified like a non-dimensional ground effect model is only function of, you can see here, certain coefficient and then distance, d, only scalar variable distance. So what you have done is that in order to actually predict the ground effect force, full three-dimensional and ground effect torque of moment, three-dimensional, as a function of three-dimensional position, how you want to actually position, not just distance or z height, but also x, y position, also velocity, x dot, y dot, z dot, because you might actually have a different ground effect when you approach it ground faster. And also attitude, because you actually land in a different orientation, it might actually generate different ground effects. So end effect is that you train the basically prediction of unmodeled ground effect forces and the torques, and then you added that to your controller, and we are nonlinear control experts, so we can actually design the nonlinear tracking controller that can track various trajectory, including very close proximity scanning of the ground, as you can see here. So this is not possible with a conventional controller. And also even going over the table, because all of a sudden, when you go over the table, you're going to experience the ground effects, and then our neural lander controller can easily handle it. But this is an offline control where you train the very complicated deep neural network to predict the ground effects. But the next step is obviously, so we'll have two extensions. How can you extend this kind of a prediction of aerodynamic interaction with maybe other neighboring aircraft? And you have swarms of drones that have to fly in very close proximity. So that's called a neural swarm. So this is another paper with Gwanya and my postdoc worked on, and also in collaboration with Yisung. So we kind of trained the network. So it looks like this video is not working. That's fine, because essentially you have seen this like how many of these 16 quadrants are flying in random motions and then control. So we designed the neural network. The thing is that it actually should be permutation invariant. What I mean by that is that when you have like two neighbors, it doesn't really matter which neighbors are which, right? So in that sense, it has to be permutation invariant, and we actually leveraging this particular technique called the deep set to actually have a permutation invariant neural network. So somehow video is not working. That's fine. So the result is that we have a very like path rulers flying closer to each other, much better, because you don't see any this kind of aerodynamic interaction, because we can correctly predict that aerodynamic interaction when you have a drones flying close to each other. So we have this experimental video, and sorry about that, it's not working. Then another extension we are doing. Okay, so I'm gonna stop. Sorry about that. I'm gonna restart the presentation. So sorry about that. I'm gonna just use the video. So this is the, hopefully you can see the video. Yes, Ben? And then right video is basically our neurosome-based control that actually shows better performance when you each drone's experiencing downwash, and that's what deep neural network are handling. And then we have basically extending this neural swarm and neural lander. Now we have real-time version. Okay, you train the deep neural network to predict some wind-based disturbance. But the thing is, those ground effects or like interaction with the neighbors, so it's kind of a state-based. But what if you have a wind that's kind of completely independent of your own state? No matter where you are or what kind of motions you are doing, the wind blowing by externally is not actually controlled by you, right? Your drone. So what if you have external disturbance that's completely independent of your state? And then in that case, you have to update your prediction of your model, learning model. Here, this is Gwanya and Michael with Isong and Anima, and essentially, and Kamir. And essentially what we are doing is we decomposition of this kind of a learning model as a kind of a disturbance, and it's a function of a state, and there's a component that's a function of only time, and there's a component only function of a certain, like a deep neural network, where A here is being adapted in real time. So it's kind of a combination of real-time like learning with offline learning, which is kind of very powerful to handle very challenging model errors or disturbance. So we'll see where we headed after this, but I'm very excited about this future direction. So in most mathematical part of this my talk, so I talked about a lot of stability and proving the, okay, you can kind of bound your AI black box kind of output, and then you can actually do some real-time motion planning using sequential complex programming. Then how can you actually tie all these things together using some stability theory? So that's actually basically contraction theory. So many of you are familiar with a nonlinear controller. Essentially, the Lyapunov function is like this. You can find some scalar function, and then if that scalar function is decreasing over time, your system is stable. It's almost like you can check the eigenvalues of your linear system. What's new is the contraction theory. It's actually kind of motivated by fluid mechanics. So you actually get the differential a path, path interval. If that path between these trajectories are contracting in terms of like a volume, then your path, your system is exponentially and globally. Globally means that from any initial condition, they are kind of coming to each other. So as opposed to this Lyapunov-based approach where you characterize the stability of an equilibrium point, we are actually concerned about multiple trajectories here, because I told you that we have many, many different trajectories from the swarms of a spacecraft, or you have a single spacecraft tracking certain desired trajectory, and you have your own trajectory, you have a desired trajectory, it's a tracking control problem. So for that, how you can actually quantify the contraction? So that's actually this mathematical notion, but this bottom line is very simple. You get the generalized Jacobian over your linearized dynamics. Hey, we know the linearization technique from Lyapunov indirect method. It can get you only local stability of our local equilibrium points. But this one, what's new here is that it's actually global, means that it's actually from any initial condition. If you can prove this generalized Jacobian in the red box, it's uniformly in time, negative definitely, which is actually equivalent to this kind of almost like a Riccati equation or Lyapunov equation form. The challenge here is that how you find this m or theta. You have to find that. It's almost like a quadratic Lyapunov function, but what's new is here is that your Lyapunov function is always quadratic like this. Partial x, which is a virtual displacement, infinitesimal displacement of your trajectory. So your delta x is tending to 0, and any solutions, you can see this diagram here, any solution will converge to single trajectory. So this is the method that can be used to characterize the stability of multiple trajectories. Each trajectory they are converging to can be unstable. It doesn't matter for this. What you care about is that those trajectories converge to each other. And then what's new here, I mean, not new, powerful is that we talk about the input to state stability or asymptotic stability. In my opinion, many of them actually are talking about exponential stability. So what's here, important thing is that it's actually, Feynman is actually Caltech professor, right? So we are using this Riemannian metric, which is a positive definite matrix here, M. So we find this Riemannian metric-based Curtis path integral, which is defined by R, which is actually basically integral of delta Z norm, coming from the previous slide. If you can show that R is actually exponentially converging to 0, then all the paths, all the trajectories from this nonlinear differential equation, x dot f over x comma t, with a disturbance d, they are converging to each other. And if you don't have a d, then it's converging to each other perfectly, exponentially fast, or it's going to converge to the bounded bore. Remember, I said the bounded bore, and that bore, that's kind of steady state error, can be used actually to generate this cube. And that cube is actually kind of your uncertainty state robustness bound coming from your nonlinear stability analysis. You can actually feed back into your learning and also optimal motion planning. And in fact, that's exactly what we are doing. I mean, I have to say this one about this. This is actually also involved in NASA Center Innovation Fund. It's actually asteroid redirect mission. So for Dimotakis, as a JPL chief technologist, was actually spearheading this effort. I was responsible for nonlinear attitude control. And we developed some very powerful nonlinear attitude control. I want to just mention that here essentially it's adaptive control, but integral control can get you that robustness that can carry that. So I'm going to jump a lot of this. So when I look at this like an estimation problem, estimation is basically you have a sensors and you go to the robotics community and so on. They assume that they have to use Kalman filter variation, extended Kalman filter, or low dimensional state, you use particle filters. What he actually found is that, hey, what he can actually leverage this contraction theory and nonlinear stability analysis to design the observer that can actually be stable for a variety of nonlinear dynamics and nonlinear systems. So that has been my contribution here, where I actually developing some vision-based navigation using high-dimensional features. And it's unfortunate that I cannot show any of this for spacecraft application. There are a lot of excellent work going on at, let's say, Harvard and Kai Masilka and Vicencio. But here is the thing. How can you extend this contraction for the stochastic dynamics? Now you add a noise, and then your deterministic linear dynamics becomes a stochastic differential equation. Surprisingly, if your original dynamics without disturbance, without noise, is actually contracting, then you can see that your noisy trajectory here in the blue box is exponentially bounded in the expectation sense. So its mean squared error is actually exponentially bounded. So what he took here is that it's a very rigorous kind of analysis where you have nonlinear dynamics and deterministic noise, and the stochastic noise essentially is a white noise. I mean, here you saw the amino process right there. And you can take this kind of error bound C here, and then you can try to optimize in real time. So this actually a departure from the conventional stochastic linear or linear Kalman filtering with a noise or AQG type of controller, because what you are minimizing here is that steady state error. And if you can optimize that in real time, you can design the very powerful robust controller. So we designed the robust controller here that actually minimizing the cost function, and it's actually turned out to be convex optimization. And you can see that it's the nonlinear observer with a stochastic noise and so on, because it's an observer problem or estimation problem. You can easily outperform the extended Kalman filter. And this our new extension with the Hiroyasu in CDC 2009 and transactional automatic control, we actually improved this cost function and then some of the convex optimization problem, so they can actually get you better result for both optimization-based control for nonlinear stochastic dynamics and so on. So I want to just quickly mention that some new exciting dimension is that when I talk about the neural network and stability problem, you can also use a deep neural network here. Actually, we are using a deep recurrent neural network for the LSTM to generate the stability function. You can view this as a control function, but we are essentially finding the contraction metric, this positive Riemannian metric function, to even generate the stability proof without solving optimization problem in real time. Another extension we are doing is that maybe I have 1 minute. Is that, okay, I talked about the stability problem, how you use a deep neural network to even prove the stability, nonlinear stability of nonlinear stochastic equations for nonlinear estimation or nonlinear control or for optimal control. And also I talked about optimal motion planning and how you actually use the learning to benefit both motion planning and feedback control like a neural lander. But here, we are also doing motion planning using learning. So what we are doing here is that our guest PhD student, Dan and Wolfgang and Wido Isong, we have an expert demonstration using imitation learning. It's essentially using deep neural network. And then, but you cannot use the kind of real-time variation of your sensory information. So you need to use some local information. So we kind of use both a sequential convex programming, so conventional optimal control-based approach with a deep neural network-based approach to do a motion planning. So this is a kind of already published in the robotic automation letters. So in closing, I think we have a bunch of these boxes here: optimal feedback, nonlinear estimation, and typically stability was kind of more of a feedback control and estimation problem. But we can bring this rigorous stability analysis for nonlinear, and I emphasize stochastic dynamics to both designing the motion planning, so that we can basically use the chance constraints and stochastic nonlinear dynamics in your motion planning problem. But the thing is that motion planning is as good as whatever model you have, so you can improve your optimality and performance and robustness in terms of collision avoidance, safety-based trajectory using this learning-based method. And obviously learning-based method will be very beneficial to improve the performance and robustness of your very challenging mechanical robotic systems like a flying ambulance that's making a landing in the presence of turbulent winds. So I think in closing, it was a very exciting endeavor to work with the machine learning faculty, robotics faculty, and fluid dynamics experts in CAS and GALCIT. I think we can actually play a very important role to map out this future direction of autonomy from the robotics and mechanical and aerospace field. So thank you so much. And with that, I used the full hour.